Okay, let's go for the next experiment. It is gonna be RC circuits. In this case, let's see what happens when we discharge a capacitor. Discharging a capacitor. In this case, we take a capacitor with a resistor in series connected to a battery. Correct? We have two switches, right? This is switch 1 and switch 2. Okay, in this case, we have that these two components are in series to the battery. Now let's remove the battery, means let's open switch 1 and close switch 2. Okay, now we have the charge moving right around this loop. Remember at the beginning, if this is positive, right, it's negative, it becomes charge positive and negative, correct? Now when we remove the battery and we close this switch, right, we have current going, let's say, from positive right to negative to get the equilibrium. Imagine that we have not this resistor, means that the discharge should be very fast. But because of the resistor, the time of discharge stays for a while, right? Depends on what? Depends on this resistor. Also, we'll see later, depends also on the capacitance. Okay, great. Now let's go to this part of the circuit, right? And let's apply the Kirchhoff's rules of the loop, right? And we take only this loop, right? We know that the voltage drop right here is gonna be charge over the capacitance minus right current time resistance, and give us the voltage drop right here, correct, equals to 0 according to this loop rule. Right, now we know that by definition current is a change of charge respect to time, because the current decreases when we are discharging, that change is going to be negative. Great, now let's apply this condition right here and let's arrange it, and we have this equation right here. Let's use the integral because we're dealing with these derivatives. Okay, when we do the integrals, we have, right, this equation right here. Later, right, it becomes this equation, charge equals to initial charge e to the negative t over RC. Perfect. One more time, we know that definition of charge, right, is change in current respect to time. Again, in this case, we are discharging, so it becomes negative, correct? Now let's make the derivative of this quantity, which is charge respect to time, and we get this quantity right here, correct? Now what do we have? Look, we have current equals to Q naught over RC e to the negative and negative t over RC. Now if we send this R to this part, right, what do we have? Let's arrange it, and we have current and resistance, about the voltage, and what is this? This is also voltage at the beginning, right, when we use capacitance and the charge. Okay, perfect. Now it becomes, right, this equation right here. Great. Now let's apply natural log, right, to both sides, because we're looking for the time in this case. Wait, when we do that, we create this equation, and that's the equation that we are gonna use in this experiment. Okay, in this experiment, we're looking for this RC. This RC is called the time constant. Okay, so the resistance times the capacitance is the time constant. Let's check it, let's prove it. From the theory, of course, it's gonna be just R times C, but from the experiment, we have to plot, right, the voltage, how voltage changes with time, correct? And let's apply then this equation. It's gonna be similar to a linear equation. It's gonna be like a y equals to mx plus b, correct? So let's plot again natural log of voltage, right, against versus time. Okay, to get the equation like that, like this one. Now the slope, if we compare again, we compare the linear equation to the slope right here, which is negative, we see that the slope m must be equals to, right, 1 over RC, or equals to 1 over tau. Tau again is the time constant, correct? Then from the graph, we call this times constant as the experimental one equals to 1 over the slope. So for this experiment, we need to find the slope. Okay, now let me show you how to do in the experiment. It's coming right. Okay, for this experiment, we need these 2 tables, right? We need 2 cases. And this is gonna be the capacitance for case 1 is gonna be 100 microfarad, right? And the resistance is gonna be 100 kilo ohms, right? In this case, we start with a voltage of 1 barre, right? It's about 1.54. Depends, sometimes changes. It will be right like a 1.50, 1.54. Just pay attention on the video to see what is the starting voltage. Okay, and we are recording the time. Correct, this is at the beginning when time is equals to 0, right? And then we are gonna discharge the capacitor, and the voltage gonna be right decreasing, decreasing, decreasing. And let's try to track right the voltage, right, and the time. More or less it's gonna be the voltage, right? Imagine the next one is 1.20 or could be 1.22. Depends, because the change is going to be very slowly, right? So try to see when is a voltage close to this one and find the time, right? The next one is going to be 1 volt, right, in the time, right? 0.8 volts in the time, right, and so on. Again, this voltage is going to be as a reference, not necessarily going to be the same, but close to these quantities to have, right, a control, right, of the voltage and the time, more or less. Perfect. This is for case 1, case 2, the same thing, right? Now let's double the capacitance and let's double the resistance. And let's see what happens to the time. Is the times double or not? Let's do it. Perfect. The same thing. Let's just start with this voltage at equals 0, and then let's track the time when the voltage, let's say, takes about 1.20 volts, 1 volt, right, and so on. Later, we have to plot these 2 quantities, or to plot natural log of V, right? We have it right here. We have the initial voltage. Now let's look for ln right here, correct? And let's plot ln voltage, right, versus time, correct? Then we expect this slope. The slope is related to the experimental times constant. Okay, so this times constant experimental gonna be 1 over the slope. Let's compare this to the theoretical value, which is from the theory. It's gonna be the resistance times the capacitance, correct? And at the end, please let's find the percent error between, right, the experimental value and the theoretical value for these 2 cases. Okay, now let me show you the real experiment, the times and the voltages that we were supposed to record, right, to be used on these tables, and later to be used on the graph using maybe Excel, right, to find the slope for these 2 cases. Okay, let's do it. Okay, this is the circuit that we are using today. We have 2, let's start with case 2, right? We have 2 capacitors, right, 1 and 2. These are in parallel, means that the torque is gonna be the sum of each one, and we have the resistances right here, right? These 2 are in series. This is 100K plus 100K is 200K, right, for the resistances. As you can see, right, we have again 2 capacitors in parallel, and we have 2 resistances, correct, in series. Capacitors are each one 100K, correct, so we have 2, it's gonna be 200. The same thing for the resistors, 100K each, right? And now let's use the battery, correct, connect the battery to charge the this capacitor, which in this case are 2, but they are in parallel, makes 1, right, the equivalent, correct? Okay, so this is the battery right here. This is gonna be the clock or watch for us. Why the another cell phone, right? And let's track again the voltage and the time to use those that data to find the times constant. Okay, let's do it. So we have then let's charge the capacitors, correct? Okay, let's connect this to the battery. Can you see? Okay, perfect. Now let's connect the voltmeter, right? One goes right here and another goes to the other side, right here, correct? And see what do we have. We have what? 1.50. It's negative, but let's change the polarity right here. It's gonna be on this. Okay, let's leave this one right here, correct? We can switch them from here. See, from here. Okay, to make it positive. Okay, we switch the direction of the current. Okay, now it's positive. See, more or less the initial voltage is gonna be 1.54, more or less. Okay, great. Now let's see what happens. Let's start the time at the same time that we disconnect the battery. Let's see if we can do it. We can do it. Oops, sorry. We can do it at the same time. Okay, let me try to do it at the same time. Okay, 1, 2, 3. Okay, as you can see, the timer here and the voltage are going down. While the voltage is going down, the time is going up, correct? Okay, again, let's try to find the time when voltage is about 1.2, right? 1.8 volt, correct? And so on. Perfect. It takes for a while, correct? Great. Okay, we are already at 0.50. Okay, so this is the time in seconds, correct? Perfect. I can't believe it. We are doing it with these tiny elements that I bought 3 weeks ago. Okay, great. Perfect. It's coming. Great. Remember, we're looking to what, 0.2, more or less 0.2. We can go farther if we want to. Okay, we can do it. Let's go a little bit farther just in case we need more points, because at the beginning is not so accurate because it's very hard to start right both devices at the same time. Imagine that we go to 0.1, right? Okay, now let's start right here, and this is case 1. Yes, we did it. Now let's go to sorry, it was case 2. Okay, case 2 is one more time. We have 200K, right? Microfarad, right? And this is 200K K ohms for the resistances. Okay, this is case 2. Now we are going to case 1. Okay, to that, let's remove one of these capacitors, right? Because we need only one capacitor with 100 microfarad. Also, let's remove one of these. Can you see? Okay, these resistances, correct? Like this. Now let's go back this resistance to the battery. Okay, let me do it. Okay, I did it by myself. Let me see, it's correct. Yeah, it looks correct. Okay, so this is case 1. We have a capacitor of 100 microfarad and a resistance of 100 kilo ohms, and we have the battery, the same battery of about 1.54 volts. And repeat the procedure as before. Correct. Let's do it. Let's repeat it and find the time constant. Great. Okay, let's do it again. Let's go back to the voltage. Okay, the time, let's start the timer. Okay, now let's go to the battery. Correct, let's connect the battery as before. Right, to find the initial voltage as we did before. Correct, yes. As you can see, this experiment is very easy, very simple. I can't believe it how we can make this experiment with these small devices. Okay, hopefully it's gonna work. Okay, the same thing as before, right? We have a capacitor in series with a resistance. It's charged already, right? The voltage is 1.54, and now let's discharge it and find the time constant from the experiment. We already have it from the theory. Okay, let's do it again. Let's start at the same time, right? The discharge. Okay, let's do it. See, we're paying attention right here on the time and on the voltage. Must be close to 1.20, 1.80, 0.60, 0.40, 0.20. Right, see, this goes very fast as you can see. Correct. And we have again the discharge for this capacitor. Perfect. Okay, let's stop right here. Okay, let's just stop right here. Correct. And again, with this we finished this experiment. Now please plot the data, natural log of voltage versus time to find the time constant. Okay, see you in the next experiment. Thank you.